Hello again. My name is Engin Kayraklioglu. You're not supposed to hear it. It's for recording. You're hearing me though, right? Okay. So my name is Engin Kayraklioglu. I'm an engineer in the Chapel team at Hewlett-Packard Enterprise. And this talk is about me trying to make the case for compile languages for HPC. And the way that I will do that is talk about some of the compiler optimizations we do have in the Chapel compiler. Proceed. All right. So I think we covered this pretty well, but I still wanted to include it for completeness. Chapel is a programming language. Parallelism and scalability is first-class kind of citizen. That's how it's designed. Chapel is portable. It can run on different operating systems, networks, architectures. It's general purpose. It's not designed for a specific domain. We have users from many different domains. It's a modern programming language. What I mean by that is it has things like object orientation, error handling, memory and type safety that are completely orthogonal to parallelism and performance, but we do have those kind of features as well. And obviously, we are an HPSF member, an established project under HPSF. Everything is open source. So one of the points that I'm going to be making is that expressiveness in the language helps the programmer, which is kind of an obvious thing, but also it helps the compiler, which is a more underappreciated fact. So I will work with a couple of examples of like Chapel code. The first one that I have here might be a little bit familiar from Jade's demo. This is a loop, a for all loop that is parallel and potentially distributed. Well, the array is distributed, so it's a distributed loop. And I could just pick up indices of this array and then access this array using that index. So because this array, as the name suggests, is a distributed array, what we can do is we can take a fast path if the index I is local, and then do a basically pointer offset, which would be zero cost, essentially. Or if it's remote, we would just take the runtime path, which could incur some communication. So even if you are taking the fast path, you are still paying for that dynamic check to see whether index I is local or not. And this is a cost for high-level abstractions that you're paying. Your code might be a little more complicated, so this is pretty similar to what I had before, but instead of accessing index I, instead of that, I'm just doing some computation on I, which could give me a random index. So that could result in fine-grained access on this distributed array, which would result in fine-grained communication that is really terrible for your scalability if you're running on multiple nodes. This is, again, a perfectly legal Chapel code, something that Chapel allows you to write, but then at the same time, it can incur a lot of overhead because of that high-level abstraction that is distributed arrays. Last but not least, it doesn't have to be fine-grained communication. So Chapel has really expressive high-level array operations. So this is, again, a perfectly legal Chapel code where I am trying to slice an array, distributed array 2 on the right-hand side, from indices A to B, and then copying that chunk into indices X to Y in another distributed array. So you can write code like this in Chapel. And it will actually do bulk communication, so it's not going to be fine-grained. So that bulk communication side is fast, but at the same time, these array slices, as we call in Chapel, are really powerful. They can behave as arrays. You can pass them to functions that accepts array arguments. You can iterate over them just like their arrays. So we really need to have a way of expressing those array slices in Chapel, and that's a high-level cost that you have to pay. So if you are doing these kind of copies in Chapel a lot in a tight loop, where the data that you copy is like 1,000 elements or so, like really small, then you will see the cost of creating those slices. So this is, again, super expressive, super nice as a programmer to be able to write stuff like that. But if your data is not big enough, then you will get bitten by the performance. So this is a very common problem. High-level abstractions. Oh yeah, please.
I said at the very beginning, when you do the for all, that your array data is already distributed on each node.
Correct.
So in the case you specify in the beginning,
right,
should be on each node, right?
So index I for distributed array will be all local access. Yes, there won't be any communication for it, if that's what you're asking. If you have the first snippet, there is no communication there. But for each access, you are paying a cost to check if it's local or not, unless you optimize it.
I saw in one example, Jed showed that in the local domain, right?
Was it local?
No. So the difference is there's a, like, without optimizing anything, the runtime will have to say, is I a part of the local set, and can I just, essentially access the pointer, or do I need to say get the remote memory? That's the naive, just like here's a loop, even though we know it's running on each node. What you saw in my demo was there was no communication for the parallel loop because of these optimizations where we say, okay, we don't need to check whether we're local or not, we know we're local, and can just do a pointer dereference. Does that help?
Yeah. But there has to be different syntax for all loop, right?
Right, that's a different syntax between the for all and the for.
Yes. So this is particularly for all. It has to be for all for these optimizations, the optimizations that I will talk about to work. Any other questions here while we stop? All right. So the common problem here is that high-level abstractions incur execution time costs. They are really beneficial for the programmer, but we are paying the cost of execution time. And I think high-level abstractions are good as long as your compiler and runtime are capable of exploiting those kind of abstractions. So let's begin with the first example here, the example that we were just talking about. So I will use the stream triad, HPCC stream triad. I don't know if you're familiar with it, but it's a relatively simple operation. Oh, this is timed. OK. So what this does is basically a simple vector operation. So the first two lines declare a domain, D, and then three arrays, A, B, C, using that domain. And that domain is a block distributed domain. So the first way of implementing stream triad in Chapel, a really simplified version, is you can literally use whole array operations. So these three lines, assuming that new block DOM is there in the scope, is just perfectly valid Chapel application. You can write this, and this will be a distributed operation. Stop moving. It's just spoiling it. Another way of writing this is using an explicit for all loop, and you can zipper over distributed arrays. And you can see on the right-hand side that the efficiency of this is near 100%, these two idioms. And the another third way that is perfectly legal is just to iterate over a domain and then index each element of the array using I. And before the optimization that I will talk about that we call automatic local access, this will actually reach slightly below 50% efficiency. So half as fast, basically. And this is really kind of bothersome because it's a really simple application, but you are paying for that cost. So if you have an idiom like this, what would happen is for each of these three array accesses, what we will have in the standard library is a much more complicated version of what is there. But for each index, we are checking whether the index is local. If so, we do local access, which is just a pointer offset. And if not, we are just going through the runtime to potentially handle communication. However, this is redundant. Why is that redundant? Because we know that the for all distribution, or the domain that for all runs on, is D. And D also happens to be how arrays A, B, and C are distributed. So in other words, for all will execute in the same way the arrays are distributed. So this will be a perfect locality. And technically, the whole information is right there, right? You can see the arrays definition. You can see that the domain is D, and then D is used in for all, and then indices are perfectly aligned. So this first optimization that I will talk about is precisely does that in the Chapel compiler today. So with that optimization, what we will end up with is the same exact code that I showed before that was problematic, also reaches almost 100% efficiency. And with that, now all these three idioms that are all perfectly legal and could be usable in different scenarios perform the same. Yes?
Is this below the efficiency of the first idiom? Was it 100? Was the first idiom also 90?
No, they hug each other at 96% efficiency, yeah. And this efficiency, I don't remember, but I computed by just memory bandwidth available on the hardware. Mm-hmm. So it's almost 100%, right? It's just 96%. Small gaps can happen. All right. So this was Stream. Stream is kind of a toyish example. Another case where we run into this is NAS-FT. So this is NAS parallel benchmarks. And this is a Fourier transform benchmark. Before this optimization, our kind of standard accepted version was looking like the one on top, where we'd have the explicit local access calls on each distributed array instead of doing indexed access. And it was kind of gruesome a little bit, right? Because this core kernel of the operation is really tiny actually, but it's dominated by local access calls. So after this optimization, we could remove those local access calls without having to lose performance. And before, if you were to remove them, you would see a gap or you would see a drop in performance with NASFT. This is still a benchmark. Motivating application for this was actually Chapel Ultra, and this is actually an astrophysics application. It's ultra-light dark matter simulation, which I have no idea what it means, but it's really cool to say. So this application was also kind of riddled with local access calls, as I was showing before. Particularly, I don't remember the number, 80 places in the application where you would have local access, dot local access, dot local access. So it was really making the code almost unreadable. So after this optimization, we were able to remove almost 60 of those, where around 20 still remains because of more complicated scenarios where the compiler is unable to detect. But still, this is 75% of the calls removed. Yes?
Why were they there in the first place? Was it because the user tried to be smart, or was it because there was a time in the past when this was the faster way of doing it?
Yeah, the latter. So before this optimization, the user was struggling getting good performance, and adding those explicit local access calls was the solution that we proposed because we didn't have this optimization in place. So once we put it in, we can just rip them, at least most of them, out. Any other questions?
What makes the 21 cases difficult to optimize?
So this optimization relies on for all loops, because for all is running on the iterable, and you can see the iterable and the arrays are aligned. If you don't have a for all, if you're using a low-level approach where you have co-for all and you're just spawning tasks on each locale and then spawning tasks on each core, then the compiler is not able to track that. Because there is no semantic information in the implementation that you have that you can see the alignment, unless you do really complicated analysis. And we don't do that. Any other questions? All right, moving on to the next case, which is a slightly more complicated case, still a for all, but this time the access is remote and not aligned. And the micro benchmark that I will use for this is from Bale study suite, and it's called Index Getter. It's practically a random access benchmark and pretty similar to what I was showing before in terms of like the pseudocode. It's just you have 3 arrays. One is source, one is destination, one is just random indices, and you just access the array based on these random indices. So there are multiple optimizations that we are doing in the Chapel compiler for this code to work. If none of them existed, the performance would be really bad. I guess you can scale this graph to make it look good, but you can see that there is a lot of room for improvement, and I will cover that in a second. So the first optimization that we do here, and I think that existed in the Chapel compiler forever almost, what we call unordered execution. So if you have a for all loop, it's by nature order independent because it's a parallel loop, and what we are telling or what we are guaranteeing or what we are not guaranteeing is that the order will execute in any order, right? The loop will execute in any random order that can happen based on scheduling. So based on that information, we can see communication calls in for all loops to be potentially unordered. And what we do for that is we invoke a different runtime function that is sort of non-blocking under the hood, so that the runtime and the communication layer can schedule calls or communication more freely. So this gives us a huge bump actually from where we were before, but that was still not enough. And one of the reasons that this was not enough is actually Arcuda sorting. This is similar to some of the sorting routines that Arcuda uses, and this benchmark case was very similar to it. And both for Arcuda sorting and for this benchmark, what we implemented and added to the Chapel interface is data aggregation. So we literally have a copy aggregation module that you can use in a fashion similar to this one, where you define aggregator objects that buffers the data. So if you have fine-grained communication like this, the aggregator object will buffer the data and flush it when the data size is large enough, so that you do bulk communication instead of fine fine-grained communication. And when you do that in your code manually, you reach the performance that we wanted. So at this point, I think we were comparing against Shimem implementation of the same benchmark, and we were beating it at this point. So Shimem is, I think, was between mid blue and dark blue. But this is still a manual modification to your code, which is less than ideal. And then the question becomes, well, can we make this transition automatically? And it looks like the answer is yes. Because there are three parts of answering that or implementing that, is whether it's safe to complete the communication in any order. The other question is whether one side of the communication is local so that it can do the aggregation, and whether you literally have means to aggregate the data. And luckily, by the time we added this automatic aggregation optimization, all three questions have answers. They were just not tied together. So we had this unordered for all optimization that I referred to that does the safety check for us. We had automatic local access that actually checks whether one side of the assignment is local or not. That's the first optimization that I covered. And the means to aggregate the data is aggregator objects. So it was mostly just tying these or connecting these three dots together to come up with this new optimization. And this optimization is in the Chapel compiler. It's not on by default, but you can throw a flag. And if you throw that flag to enable the optimization, then the straightforward index gather performs identically to this one and beats the reference Shimem version. So thanks to that effort, now this simple implementation, I think it's as simple as it can get, performs better than the reference version back in the day. Yes, Jade?
What prevents it from being turned on by default?
Because it can fire more aggressively than it should. So if the automatic aggregation fires in a case where both sides of the assignments are local, then you would be paying for aggregation cost that doesn't have anything to do with communication. You would be just going through the buffer and then copying the data back locally without any communication at all. So there is no way for us to, not no way, but currently there is no way to tell both sides are local. If both sides are local, we need a bypass aggregation, so to speak, that does no op. And we don't do that today. So you'll be paying extra if that's the case. And you would see performance degradation, actually. Yes?
Could you talk more about where the copies are inserted? Is it for every assignment, basically?
Yes. So copy calls in the transformation, copy calls are inserted just like that. Mm-hmm. But when that copy call happens, what happens under the hood in the standard library that implements aggregation is just it will copy the data into a local buffer first. Mm-hmm. And once that local buffer reaches some size, I think it's 4 kilobytes in some architectures, it will flush. So it will send the data.
Yeah, I guess the part that I was asking about is like what, we have the original code and the bottom code. Like what rule applies to turn the D equals something into add.copy D, right? Is it every assignment that gets turned into this?
I see. So it's basically dependent on first two questions here. So the unordered for all optimization dictates that it has to be a for all loop. B, it has to be the last statement in the for all loop. Because if it's in the middle of a big loop body, then it breaks order independence. But if it's the last statement, you can execute it at any place. So that's the first question. The other question is, thanks to automatic local access, we should be able to tell one side of the assignment is local and the other is maybe local. If the automatic local access can tell us that, then we inject the ag.copy call there. It's a big transformation, but analysis is probably more complicated than the transformation. Yes?
And I guess you can't have loop carry dependencies. Or can you go back into the buffer and get it from there back?
No. So that's the first question here, right? So A, for all guarantees no order dependence.
Oh, that's right. Yeah.
Right. This wouldn't fire in a for loop. Yeah.
So adding the locale check, is that expensive that you can't do it by default to avoid the local? Like to do the local optimization?
It will probably be some costs, but the reason that we haven't implemented is because we didn't get to it. So there's no like major roadblock as I'm aware of. It's just hasn't been prioritized.
I believe that implementation can happen solely on the aggregator object
Yes.
side of things. It doesn't have to, like, there's nothing special about this aggregator object. It is pure Chapel code.
Correct.
And I think that optimization can just happen there.
Right. So there should be a way of aggregators to turn themselves into a no-op aggregator. We even discussed like dynamic strategies. For example, you aggregate 1,000 copies, but 950 of them are local. So maybe even you take that 50 remote fine-grained access and turn it into a sort of like a bypass aggregator that doesn't do anything actually. So we need some kind of smarts like that we haven't prioritized implementing basically. Yes?
I'm also curious, like the slingshot network tech is supposed to be pretty good about this fine-grained type of
Correct.
communication. Is the benchmark that you're showing us, was that run on Slingshot or in InfiniBand? And what's the, like, is there a difference in performance there?
Yes, there is. I don't remember exactly which machine this was run on. Based on number of nodes, I'm going to guess this was an EX or the XE system. It was an XE. So it's an earlier generation than Cray EX. But for the question that you ask, you are making a good point. I think our aggregator module has special tuning. So if you are running on an EX system which has lower latency, then the aggregation buffer size is different. It's smaller so that you can issue more communication without having to allocate more data for buffers. If you're using InfiniBand, our buffer size is bigger because the latency is higher on InfiniBand. So we do a little bit of tuning for that. It's not like too complicated rocket science, but yeah.
But it still helps to apply this optimization on Slingshot.
Yes, definitely. It's not that fast. Yeah. Any other questions? Right, the application motivator for this was Arcuda actually, the application that we were talking about. And as I alluded to, aggregators were implemented for Arcuda primarily as well. So there are many uses of aggregators in Arcuda, and I'm just looking at the numbers here. 61 places used aggregators, and 40 of them almost, or 39, we removed. Because of this optimization, or can remove. We haven't actually removed. One interesting thing is we also discovered 3 other places that aggregators could actually be used, but weren't used. Probably it was because not something that was optimized. So we added those uses as well in the Arcuda code. So this is also another potential benefit of relying on your compiler to do the optimization rather than relying on the programmer to do the optimization. And again, there are many complicated cases here where the compiler cannot detect, like nested coveralls and a for loop and things like that. My slides are so impatient. All right, last one. So this one is a bulk copy, but it has some constant cost. And this is the newest optimization that we've added in the Chapel compiler, or at least the newest one that I will talk about. So let's look at this simple example. And this is a full Chapel code. First line declares 2 integer arrays, one based from 1 to 10. And then the second line assigns a chunk from B to A. This is sort of like a memcopy, if you will. But if you write an application like this, what happens under the hood? Okay, this is the pictorial depiction of the operation. So we are just copying a chunk from B to A. What happens under the hood is we need to represent these array slices that doesn't own any data but refers to an existing data as if they were arrays, because they are really powerful. As I said, they behave and they look like arrays in Chapel. So we really need to keep that expressiveness. In order for us to be able to do that, we create a record and then a class in it. So these are Chapel-specific terms, but you can think of it as like a statically allocated struct in C and then dynamically allocated struct in C. And dynamically allocated struct is class. And for each class you need to, and record too, you need to initialize them. And then what happens is we have this bulk data movement machinery that works for Chapel arrays, and we can just pass these kind of encapsulations to the bulk data movement machinery as if they were arrays, and it will just handle the memcopy for us. And that memcopy again will be fast. But then again, you are still paying for the cost of creating this kind of structure here for each side. So we again create a record, a class instance, and then under the hood we also have to create this domain 3.8 so that we can do math on it. But long story short, this results in 4 dynamic allocations and 4 rather complicated initializations. Now, if you are moving large enough data, that doesn't matter. But if this is in a tight loop, which happens a lot in user code, and you are just moving like hundreds of elements, then that cost is very visible. So, and that cost is meaningful because, as I said, these are array slices behave like arrays, so we need this kind of structure so that they are fully functional arrays. But at the same time, in this particular example, which is really common, they are rather ephemeral, right? We don't pass them around, we don't create variables to keep them, we just create them and they are just destroyed. So do we really need to create that structure? That's the gist of the optimization. So what we do in the compiler today is we create a very simple rudimentary proto-slice record, as we call it. So now these types are not visible to the user at all. This is just a compiler-generated type, or rather compiler-used type. So this just sort of encapsulates the expression rather than creating a whole array view. And we modified this bulk data movement machinery that is under the hood so that it can handle these proto-slice records. So with that, we don't have any dynamic allocations, and the initialization is just basically a couple of assignments. And this significantly reduced the overhead for a very common operation that is super expressive that our users like to use. So let's see the benefit of that. This is a rather crowded plot, so let me walk you through it. The gray bars, okay, so the plot on the x-axis has data size, so this is the number of integers I'm moving in my assignment. Y-axis is relative throughput, so higher the better. The gray bars are for loops, so you can do the assignment using for loop, which is a fallback mechanism many of our users do for small assignments like this. So it's always 1. All my performance is relative to that for loop. And before this optimization is purple. So if you look at, for example, 10 element copies or 100 element copies, the performance is really abysmal. Like it's just 10 times worse or maybe even more than sequential for loop. But after this optimization with smaller data sizes, the performance is pretty much the same. With 1,000 elements, it's actually much faster than both. And as you increase your data sizes 10 million or something, the performance is basically unchanged because you are basically dominated by the data copy cost, which is what you want to see. So with this optimization, now you can write the code in as expressive as it can be. And in any case, it will perform near optimal. All right, so let me wrap it up. So Chapel is a high-level programming language, and when you say that, it's kind of a scary statement because there are a lot of costs. But my point here is that it doesn't have to be that scary as long as your compiler, your runtime system, your standard libraries are ready to handle those high-level abstractions, and it could be even beneficial. So the 3 optimizations that I covered here are not the only optimizations we have in the compiler, the ones that I'm more familiar with, of course. And the whole goal there is to keep programmers' life easy without sacrificing performance. That's all I got. Any questions?
Where else will you find these kind of optimizations?
Excuse me?
Where else will you find these kind of optimizations?
Like other technologies, you mean?
Yeah, I would think that there's many places where you can do similar.
That's the challenge. That's a little bit of a challenge here, right? Because there are hundreds of different scenarios that you can optimize specifically. But I think like common cases are really very common actually. So just helping them helps a lot of users is I guess my point. So array slices can happen in, you can see array slices, for example, in 20 different formats. But this was really common and really like obvious case. So it's just, you just have to take them one by one a little bit, unfortunately. So you're right, like you have to cover many bases if you want to do that. But I think it's a good aspiration to have to address those overheads.
I was part of a project that did similar PGAS abstractions, and it was all C++, so we couldn't do these.
Right.
These type of optimizations.
Right. And that's why it's the case for compiled languages as opposed to libraries or interpreted languages, right? Just to having that full program information and being able to do those kind of analysis can open the doors. If you just have high-level abstractions without compiler support, it's way trickier. You cannot do everything in runtime. Any other questions or comments?
Could you go back? Yeah, so here you're talking about how the reason that this kind of stopped growing between the 10,000 and 10 million elements is the memory throughput, right? Like
right.
I'm not sure. Like maybe I'm not understanding the axes right, but how come in the bar in the 1,000 element case is so high, higher than seemingly the cap that you run up against in terms of memory throughput?
1,000 integers are small amount of data that can fit in the cache.
Okay.
So if you keep running this in a tight loop, you're probably just reusing the cache.
Okay.
That would be my theory there. And this is relative throughput, not raw performance, right?
But so relative to what?
Relative to for loop.
Okay.
So if you do like 1,000 trip for loop,
Right.
it is probably much slower.
I see. Okay.
So that makes the relative throughput higher. Maybe I should have probably provided the times. I don't know the times offhand, but yeah.
Okay, yeah, the relative thing. Because I was for some reason assuming that, especially because the for loop is written 3 to 8, I was just assuming it was a fixed time kind of.
Oh, no. It's
but-
3 to 8, but
But-
extrapolated to 1,000
okay,
trips.
yeah.
Yeah.
But how explain the 100 and 1,000 the different behavior?
Between 100 elements and 1,000 elements,
Yeah.
I want to say again, this is about relativity, because if you have 100 element copy, for loop is fast enough. But if you have 1,000 elements, then mem copy is faster as opposed to for loop. Because if you do the expressive version, right, just the slice copy, under the hood what we are doing is not for loop. We are doing mem copy. And then mem copy is faster if you have 1,000 elements. But if you have 1,000 trip for loop, it's slower. That would be my theory.
So, I mean, the actual for loop is not for loop anymore, right? The black one is not for loop anymore, right?
The middle one doesn't
The
imply.
black one.
The black one is a for loop. It's sequential. It's not parallel.
Yeah, but this is how you set it to the 1,000 less. It have kind of similar like the second the before.
So what's the difference between the gray and the purple?
The purple is the expressive version, the slice copy version.
Right. But the difference between them for a small number of elements
Is the cost that.
So can I try to put it
Yeah.
in different words? We have kind of on top of this optimization is a bulk copy optimization. So for a very small number of elements, no matter what pattern you use under the hood, it's a for loop.
Right.
But if there's a large enough amount of data, like 1,000 integers, it's literally just a mem copy. And so that's why at 100 elements, it's almost cheaper to use just a simple for loop than the mem copy. Versus at 1,000 integers, there's another optimization firing that's not talked about here that's
Right.
doing a bulk copy rather than
Right.
a for loop.
Right.
And so that's why you see that discrepancy between 100 and 1,000. Does that help?
Yeah. I mean, there's some black box magic that we don't understand.
Yes. There's actually 3 levels here. So if you write code like this, the slice copy code, there are 3 things that can happen. If data is tiny, we will for loop. If data is mid-size, we will do a single mem copy. If data is larger than 2 megabytes or something, we will have parallel mem copy. So we will spawn multiple threads that would do parallel mem copy. So that would be actually faster than C's mem copy in many cases. So that black magic happens under the hood for you. And I think that's the power of just relying on your programming language stack to do these kind of things for you.
Yeah, but that depends on the actual implementation, right? For different systems, might be different.
Correct. Yes.
It's configurable.
Correct.
So
Yeah.
the thresholds
Yeah.
are configurable.
You can move the thresholds. Yeah. We basically decide on them just based on our systems. But it's knobs are available to you. You can change them to fine tune. Any other questions, comments?
Earlier you mentioned that we had 4 allocations that took place, but I only saw 2 slices. Are you also counting the allocations for the final? Well, actually, yeah. What are the 4?
So you have 2 class instance allocations for array view types,
Right.
and you also have to create a domain from 3.8 so that you can do domain magic under the hood.
Okay.
So even though the user uses a range literally there, we create a domain under the hood for you
Okay.
in
So
before the
array-
optimization.
Array record, array view class, domain record.
Correct.
Domain view class,
Correct.
domain class.
Yes. Correct. So there's a lot of allocation, memory back and forth happening. It still happens if you're using slices in other patterns than this.
Yeah.
But yeah.
How far does this go? At what point does your slice get complicated enough that you can't do this anymore? That this optimization doesn't fire?
It has to be an assignment. It has to be a one-to-one assignment. So if you had like A3 to 8, B3 to 8 plus C3 to 8, it wouldn't fire. It can. We can make it fire, but it doesn't today. It can work with multidimensional arrays and multidimensional slices. It doesn't work with things like rank change views as we have, like just grabbing a 2D chunk out of a 3D array. It doesn't work for those cases yet. And again, it can be extended to those. It's just we don't have a case for it today. That's pretty much what I can think of. It works with distributed arrays, local arrays.
But it works with like complex indexing expressions that are strided and
Stride, I cannot recall offhand. I don't want to say. I have to go back and see the code. So normally, like you can slice an array with a strided slice. Like even though the array is 1 to 10, you can say 3.8 by 2. So it will just pick up indices 3, 5, 7. That's what Jade is asking for. I don't remember. Maybe not. Probably not.
It seems like it ought not to be relevant because once you built the domain, the slicing code is the same, right?
Correct, but what I don't remember exactly is whether this proto-slice record can store a strided range and can pass it around.
you won't get a mem copy in that case, but you could, in theory, have
Right.
the proto slice rather than the allocation.
Right. It would still save you some time. Yeah. Any other comments, questions? Who's up next?
I think it's me, but not for a few minutes.
Okay. Thanks all.
Right on